All right. So is the screen visible?
Yes, ma'am.
Yes, ma'am.
Yeah. Yes. Okay. Okay, cool. So, yeah, just a quick recap. What we were doing yesterday was sampling. So this was to solve an inference problem in a base net, or more generally, you want to sample from any distribution. How do you do that? Okay. So the purpose of sampling was to, evaluate some query of this form, typically from a base net. And what we saw was, we, we started off developing from first principles, right? Like if you were given just this distribution, something like a probability distribution over colors, and you wanted to sample it, how do you do? Right? I mean, you wanted to generate samples, then how do you do? So this was the procedure we saw. And then finally from this samples, so you get a couple of samples, maybe some 100, 200 samples. What you do is now, if you want to see an estimate, so for probability that color equal to red, from the samples, what you do is you count the number of red samples, so number of red in your samples, and by the total number of samples divided by the uh, total number of samples, right? So this is what we did, and so this is a way to just generate samples and compute a probability. Now effectively what we are doing, so this is an estimate, okay, and what we are doing in the process is that you know that a probability is also an expectation. So probability c equal to red is just an expectation of the indicator, right? So the indicator function, that's c equal to red, right? You recognize this. A probability is also an expectation, right? Have you seen this in your probability class? Yes, no?
Yes, sir.
Right? So because this is a Bernoulli random variable, and so the mean of it is the probability, right? So this indicator is a Bernoulli. So it takes a value 1 if C is red and 0 if C is not red. Right? So it's like a new random variable, and the mean of that is the probability. So that's why this is true. And what you're doing by using samples to estimate this expectation is you're writing this expectation as a sum over many, it's an average rather, of many such samples. So if you have some n samples, what you're trying to do is you're seeing the number of relevant samples. So if ci equal to red, right? So if this is a sample, so maybe let me call it si. So because s is sample, the ith sample is red. So you just do a sum over all the samples, and then it's an average. Okay. So I just thought, this is something you already know, but I just thought I should make this point clear, because this is what is the foundation for sampling, and we will use this when I talk to you about this likelihood weighted sampling, where there were some confusions yesterday. Okay, so the idea is just law of large numbers, and we're trying to use samples to estimate probability. So for going to a base net, what we saw was a prior sampling approach, where you cycle through each random variable in the base net. You visit each random variable in the base net in the topological sort order, and then you draw a sample from each of the conditional probability tables. And then you get this kind of a tuple containing a value for each of the n random variables, and that's what you return. And you do this as many times as you want in the number of samples. And we said that there could be a lot of samples are irrelevant in the process, because finally what you wanted to do is something like this: probability of plus b given plus j and plus m. So this was an example we took. Now if this probability of plus j and plus m itself is a very small value, sometimes it's even a zero value, right? Or very close to zero. So then in that case, you have to run this. You have to draw arbitrarily large samples to get some reasonable estimate. Okay, so that's what happened here. Like for the base net that we were considering, if you look at why it happened, I showed you a demo where with just 100 samples, it said that it's not able to make an estimate. The reason that happened is we were trying to get the probability of plus b given something plus j plus m. Now, the number of times plus b, the probability of plus b occurring is very small, 0.001. right? So most of the times it was that minus b came, and very few times you got this. So that's the reason why these kind of issues happen. So I just thought I should point it out explicitly. Okay, so then we went to rejection sampling. So where what you do is you keep the sample only if whatever you draw matches with the evidence that you require. And if it's not equal to evidence, you just the evidence is probability of xi given ei. So did I write it somewhere? Yeah, so yeah, this exactly this, right? So this is what you wanted, and if the values you generate doesn't match with this part, you just discard. So that means here you get no sample. Okay, you discard and you quit. Okay, there is no sample, and now you have to again try to generate another sample. So this is the process of generating a single sample. Okay, now if you have been successful in getting all xi is equal to ei, then what you do is finally you return your sample, whatever was generated. Okay, that was rejection sampling. And here also there were, we saw a demo where like a lot of samples get wasted. So if you wanted 1,000 samples, effectively, if you wanted 1,000 such samples, I had to try to draw about 5 lakh samples. I mean, that many were wasted. 5 lakh samples were wasted to get 1,000 relevant samples. Right? So there's a lot of effort which is just being wasted. And then we thought, okay, so can we not waste them? Can we somehow use it rather than just discarding the samples? And that's when we started looking at likelihood weighting. Okay, so here, I just want to clarify some things because I sense there was some confusion yesterday. I'm sure Advait was not convinced when he asked why it makes sense. And also later after the class, there were some questions. So I thought, maybe generally people are not convinced. So let's just see this in more detail. So what you do in likelihood weighting is you maintain a weight for each sample. Okay, and you do this process, you go through each of the random variables. And if it's not an evidence variable, then what you do is you actually draw a sample from this distribution, xi given parents. Whereas if it is an evidence, what you do is you don't draw a sample, you force this value of xi to be equal to ei, the value that you're interested in. And then what you do is you adjust some value of the weight. So the weight is, as such, it is equal to 1. You start off with 1. But the moment you hit upon this evidence random variable, what you do is you weight by this probability. So the probability of xi equal to ei given the value of the parents. Okay, so these parents are whatever was, it can include whatever were the non-evidence random variables, or it could include some of the evidence random variables. So if it includes the evidence, if there are some evidence random variables in the parent, it will have a fixed value equal to the value that you care about. Otherwise, it will have a value that you generated in this process. Okay, so what you do is you just multiply these weights by this conditional probability, and so that's it. So finally, you keep doing this and you get this vector. This is a tuple, and the weight. Okay, so these are the two things that you get when you sample. So each sample has these x, this vector, and this number. And finally, to compute the probability that you really need, the query probability. So in our case, it was plus b given plus j plus m. What you do is you look at each sample, and by default, all the samples are going to have the j and m values are going to be fixed to plus j and plus m, because that's what you did. You forced all the evidence to be exactly equal to the value that you care about. So these will have plus j and plus m by default. Now, additionally, what you do is you look at only those samples which had a plus b. Okay, so plus b is not an evidence. It's part of the query. It's not an evidence variable. So you look at only those samples, take its weight, take the sum, and you scale it by the total weight across all samples. So all these samples again have plus j plus n. So this is guaranteed. Okay, so this is how the estimate was going to work. Now, why did this work, right? It looks bizarre. Why are we doing this weights? I mean, this kind of a weighting, right? In the most general case, you would have taken all these weights as one and you would have proceeded. But what is the meaning of doing all this? And why does it work? Okay, so let's just, to understand it a bit further, let's just take one example. Suppose I have just two random variables like this, okay, x and e, okay, and what I have is, suppose this is the joint distribution. So probability of x e is given to me like this. Okay, so this is the underlying joint, and x can take these three values 1, 2, and 3, and e takes either plus e or minus e, plus e or minus e, while x takes one of the three values. Okay, and suppose this is the joint distribution. Okay, and what I have is, I don't actually see the entire joint. What I have is just the base net, something like this, a very simple base net, which is two nodes and just one edge. Okay, now, so what this would mean is probability of x is given to me as, what are the values? 1, 2, 3. What's the distribution here? Can you tell me the probability of x?
Point 3,
So 1 is 0.3, yes.
0.5 and 0.2.
So 0.5 and 0.2. Yeah, 3 is 0.2, right. So this is the probability of x, and what about e given x, right? So let's take x, if we fix x as 1, now e can take plus e and minus e. So what are the values here? Plus e given x is 1. So basically these are
0.1
the,
by 0.3
yeah, so this is 1 by 3.
and 2 by 3.
1 by 3 and 2 by 3, right? And for x equal to 2,
2 by 5 and 3 by 5.
2 by 5 and 3 by 5, okay? And x equal to 3,
1 and 0.
yeah, so plus e minus e. So for x equal to 3, the only possibility is here, right? At when it's minus e, there's no way you could generate a 3. So this would be 1 and this was 0. Okay, so these are the conditional probabilities. Now I'm going to try to use sampling to evaluate this kind of a query, x given minus e. Okay, so suppose what do I do? Like, I'm going to use this kind of a likelihood weighting. What I would do is I'll start with x. So maybe first time I got an x as 1. So I'm going to use this probability distribution. So maybe I got x as 1. So these are the samples. So let's take the value of x here, and let's take e. So what am I going to do here now? Like, because I'm interested in fixing the evidence as minus e, I'm going to fix this as minus e for every sample I get. Okay? And what's going to be the weight here? So the weight here is going to be probability of minus e given x equal to 1. So what was the value? This, right? 2.
2 by 3.
2 by 3, right? That's right. No? Okay, so this was 2 by 3. So next, maybe I get a 2, and this is going to be what?
3 by 5.
Yeah, so the 3 by 5, so this is like 0.6. So maybe let's say like I take 10 samples, and so all these are going to be minus e anyway. So as we go in the process, we'll get x's like maybe let's say, so yeah, maybe something like this: 3, 3, 2, 1, 2, 1. Yeah, so maybe like this. Okay, 10 samples. So 5 twos, 2 threes, and 3 ones. Okay, and all these are minus e. Okay, so these were the samples I got. Okay, so the weights will be again for all these samples. What happens here? For 3
0.
and minus e, so this is 0, right? So these are going to have zeros, and wherever you had a 2.6, here is 2 by 3, so 0.6 comes here, and this one is going to be what? 2 by 3.
Last one is 0.2.
So this is minus e, sorry, right? Did I make a mistake? This is
No.
It's fine. It's fine. Okay, so these are the weights. So this is what I got after I did likelihood weighting. And now I'm going to try to estimate the values. So suppose I didn't make use of these weights, right? So then what I would do is I would just count the number of times I got let's take probability of x equal to 1, okay, given minus e. So if I'm trying to estimate this, I would see the number of times I got 1 and minus e divided by total number of samples. This was 10. So here I would have got 0.3, right? And similarly, can you tell me the value of x I got if I didn't use the weights, if we didn't use the w's? Okay, so what would be probability of x equal to 2 given e minus e if I did it this way?
0.5
0.5 and
and 0.2.
yeah, x equal to 3 given minus e, I would have got 0.2. Now, okay, let's try to compute actual value of probability of x equal to 3 given minus e, right? So probability of x equal to 3 given minus e. So this is actually the joint x equal to 3 comma minus e divided by probability of minus e, right? So this probability x equal to 3 minus e, what is this probability from this table?
0.
This is 0, right? Yeah, right. So this is supposed to be 0. Probability of minus e is anyway a non-zero value. So this value is going to be 0. But basically what I did by, not by ignoring the weights, I got a value like this, 0.2. Right? So actually, if you see what we got here, 0.3, 0.5, 0.2, this was just the probability of x, right? So this actually gave us probability of x. Okay, it didn't give us probability of x given e. So just to see this, let us understand a little more. So suppose we used weights. If we used the w, what would we have got? Right? So this would be probability of x equal to 1 given minus e. So this is the sum of weights of all samples which have 1, right? So this is with 1, and this is the sum of all the weights, right? Sum of weights of all samples. So can you tell me what's the total weight, the sum of all these weights, these entire set? So the denominator basically. So you have 3 times you have 2 by 3 coming, right? So 3 times you have 2 by 3.
5.
Yeah, and 5 times you have 0.6. So what's the value? Somebody said
5.
the value 5, right? And what's the number of times you got a 1? I mean, the weights of all those with 1. It's this value, right? 3 into 2 by 3, so it's just 2, right? So this was 0.4, right? So was that value right? If you try to compute, okay, so let's just compute these. Probability x equal to 2 given minus e, can you compute the actual value? So probability of minus e is what?
0.5.
0.5. And so probability x equal to 2 given minus e is?
0.3 by
Yeah, so 0.3 by 0.5. So this is 0.6.
0.6.
Right? Yeah, and probability of x equal to 1 given minus e is?
0.2 by 0.5.
Yeah, so 2 by 5, this is 0.4. Okay, so what you got here by using these weights matched. So this was 0.4 and this was 0.4. Now let's look at, I mean, similarly you can do for x equal to 2 also. Let's try to see this. This is the interesting case, right? X equal to 3 given minus e. So here you look at the weight of all the samples which had with 3 divided by the total weight of all samples. So here you get a 5. What do you get in the numerator?
0.
0, right? Right? So, yeah, so this is actually giving you an accurate estimate. And why did it happen? It's because of these weights. These weights and, took care of the fact that, 3 and minus e cannot occur together, right? Because, this kind of a thing happens since you're forcing the value of e. So then the joint is exactly not from what the true joint in some sense. So whatever samples you get, the XE pairs that you get from here by the samples, by all these samples, it's not exactly from, it is not, from this joint. Okay, it's actually, it's only giving you a distribution over X because you're forcing minus E, right? So this is kind of an intuition, so why you need these weights. Now, more formally, this fact about, these probabilities, or, being actually expectations of indicators, that is something which is going to be useful. So maybe let's just do that. The formal proof actually, there's something given in Russell Norvig, the book. So I'm not very, I didn't really find that very convincing. And also there was something in the CS188 also. So both these proofs were, at least to me, I was not very convinced the way it was written. So I'll tell you something to see this argument, why it makes sense in a way that, I am convinced. Okay. So, but anyway, you're free to go through the textbook also. And yeah, if you want, we can discuss that offline. But anyway, just to see mathematically what's going on here. So generally what's happening is you have maybe, like, let's say you're trying to evaluate something like this, Q given E, and there are some random variables, some additional random variables are there, X. Okay, so there are some additional random variables, X. So maybe let's just take a case where, you have a base net like this. There's X, and with that, there is a dependence on E, and together, there's again a dependence on Q. Okay, so this is somewhat, it is general because the evidence variable is coming in between. There are some parts which are not evidence, then there's some evidence, and there's some other variables also. Okay, so something like this. So this is a general base net for this network. For this kind of three random variable case. So what you're doing here is, when you're trying to compute probability of Q given E. So this is like basically Q equal to Q given E equal to, let's just take it this way. So what you would do is you would try to get this probability. So probability of Q E by probability of E, right? And let's just take each of these. So probability of QE, what you would do is you would try to marginalize over X all other random variables. Okay, so something like this is what you would do, right? And so I'm just writing X, as a single random variable here, but more generally, this is, it can be like multiple random variables. Okay, so this is what you would use. And now this is something you can do with the base net. So something like this, probability of X times probability of E given X and probability of Q given EX, right? This is what you would do. It's the most general form. Actually, there is, here we are just using chain rule. We are just using the entire general form of chain rule. The network is itself like that. Okay. So now, if you look at this, the summation, I want you to recognize that this is actually an expectation, right? So what we're doing here is it's an expectation over X. So if I'm doing a summation over all possible values of X, so it's an expectation of this quantity, right? So probability of E given X times probability Q given EX, right? Do you see this? Is this clear why this is an expectation?
Yes, ma'am.
Yes. Okay. So now this is one part. Now I can go one step further. There's also a probability of Q given EX, but note that this is a very specific value of Q that you want. I can write it in a slightly different way. I can again take an expectation of Q given the particular value of E and X. Okay. And so what could this mean? Let me just simplify it a little more. So maybe I can just write it like this: Q dash probability of Q dash given EX times 1 if Q dash is equal to Q, so that I only want probability of Q given EX and probability of E given X, right? I can, it's these both these are the same, right? Do you see that? Is this clear? Are there any
Ma'am, can you tell
confusions?
this last part once again?
Yeah. So what I did here is up till here it's fine, right? This step, the
Yes.
expectation of E given X and Q given EX. So what I'm doing is I'm just taking this probability of Q given EX and I'm just writing this as this summation. Okay, so let me just write it here. P of Q given EX. So this is a fixed value of E and there's some value of X that's there at this point. So I'm just writing this as a summation. It's a redundant sum, but let's take all possible values of Q. And I'm going to write this as probability of Q dash given EX. Okay. And I'm going to take this only if Q dash is equal to this value Q. Right? So every other value of Q, I'm going to get 0. So Q will take something like Q1, Q2, and so on up to Qk, let's say. Maybe Q5, 5 values are there. Okay, and I'm interested in particularly Q1. So probability of Q1 given Ex. So what I'm instead doing is I'm going to take probability of Q1 given Ex. I'm going to take probability of Q2 given Ex and so on up to probability of Q5 given Ex. But here what I'm going to do is I'm going to multiply this with a 0. Right? I can do this, right?
Yes, ma'am. Got it.
Yeah. Yeah. So that's just what I did here. I just replaced this probability with the summation. Okay. So what I'm doing essentially now is, so this is again, I hope you see what I'm trying to get at. This probability, again, I'm going to write it as an expectation, right? So this is there's an outer expectation over X. Now there is an expectation over Q given E. This is a particular value of E and X, okay? And the particular value here is 1 if Q dash equal to Q, right? And there is also a P of E given X, right? So yeah, so I can write it either this way or I can take this bracket outside. That doesn't matter because there's no dependency on Q here. Is this clear?
Yes, ma'am.
Yes. Okay. So now we have these expectations, right? And if we are going to, this is what we are using, right? Essentially, when we are doing sampling. So what we are doing is to estimate this quantity. What we are doing is we have like many samples. So suppose you have m samples. What would you have done? You would have taken, the total number of samples is there. And what you do is you take the sum over each of these samples and you look at this quantity. So for each of the samples, this will be it will contain an X, E, and Q value, right? And this E is fixed. That's what we did in likelihood weighting, and that's what this also means. The E is fixed. X can be any value, and there is a value of Q. So here, what you do is you only look at the cases where maybe let me call this XS, ES, and QS. So ES is always equal to E, and you look at only those samples where this is a value of Q, and you take the value of E given XS, right? So that's what this would be approximately equal to, right? And yeah, so this is actually the weight of each sample, right? This is how we computed the weights. So for each evidence, you take the probability of evidence given the parents, right? Given its parents, or just generally it can have X's and E also. This is for this very specific example that it just had E given X's. Okay. Right? So what you get here, this is 1 by m times, all the samples where QS is equal to Q, and you got WS, right? So this was this probability of QE. Now the same thing you can do for this part also, the denominator, probability of E also, you would do it like that, right? So probability of E, you will write it as a sum over X, a sum over Q. So probability of X times probability of E given X times probability of Q given EX. So this is from this network, X, E, and Q given E and X, right? And again, so here it is, you can just take, I mean, so this is like, you can move the summation inside. And, you can also club this together with this probability of E given X. Nothing changes, you can move this here. So this is just expectation over X and expectation of Q given E and X, and just probability of E given X, right? So this is 1 times probability of E given X. So if you wanted to estimate this with samples, how would you do this? So what does it boil down to if you have m samples? So each of them will give you XS, ES, and QS, right? And all the ES's will be equal to E because you're fixing this value of E. You're not sampling E basically. What do you get here? What's
1 by
this?
m and
By m.
summation over all sample.
Summation over all samples. Yeah, so because everything has ES is equal to E, so summation over all samples, P of E given XS, right? So this is how you would estimate this. So now, so this is actually the weight of the sample again. So putting everything together, right, probability of Q given E is just probability of QE by probability of E. So that is, it's just basically both these terms. You take this one and this one, put it together, right? So this is just, look at all the samples with QS equal to Q, WS, and sum over all this Ws, right? Does this make sense? Advait, this is clear?
Yes.
Yeah. What about the others? I also want to hear from.
Ma'am, I have the doubt in the last part.
Yes, Rishabh, tell me.
Ma'am, where you wrote that P of E is equal to 1 by M summation of S P of E given E of X. I think you use the formula that the expectation inside the expectation of the X is equal to E of X, I think.
So what we are using here is a probability, any probability, right? Any probability, say some C, probability of C is just an expectation of, probability C equal to C is just this, right? An expectation over the indicator, right? So here what is happening is the random variable is X and Q given EX, right? So that is taking the value of, that is playing the role of C here. Okay, and the particular quantity you want to take of the expectation, so it's this one. Instead of that, you're having a 1 times, this is like a constant, right? I mean, there is a dependency on X because, I mean, this X will come from the sample, but otherwise it's just an expectation of this quantity. So what you do is whatever samples you have, you take. An expectation is just 1 by m times, if you have m samples, number of times you got a C, right? So that's all I'm using here.
Okay, ma'am.
So generally, even if you had some other expectation, right? So let me just, so if you had something like this, an expectation of some G of X, okay, so maybe let's take G of X, and so let X be the random variable and maybe some value, there's some dependency, some Y here, okay? And I'm writing this, okay? Some function like this, I want to find its expectation. Then what will I do? I will just draw m samples of X and I will just compute, each sample will give me a value of G. So I will draw X and then I will take, the sample will have an XS and a Y. Okay, so Y is fixed. Okay, Y is not a random variable. So what I will do is I'll just take G of XS and Y, right? Rishabh, do you
Yes,
get
ma'am, got it.
this? Yeah, so it's the same thing. Essentially, any kind of expectation you could evaluate using this way of sampling. It's good you're asking. I mean, these are things that many times when you read from the textbook, things just get brushed over. Many details sometimes get skipped. So you should make this, you should get yourself, you should get these things clarified. So what about Jaishika? Do you understand this?
Yes, ma'am, it is clear.
It's clear. Maybe Aditya Jain. Do you follow this? Yes. All right. Maybe let me ask some more people. I just want things to be consistent with a good number. Divyansh, is this clear to you? Like why this is a problem? Why this method is correct? So maybe like all of you just maybe I'd just like to see, you can just type on this chat whether this makes sense. It's clear? All right. Okay. Fine. So this was about likelihood weighting, and whatever I showed you now was about why this works, why likelihood weighting works. Now, there's one thing that is probably, yes, to some sense it's lacking in likelihood weighting is that, you follow this base net structure. Like when you generate your samples, you follow the base net structure and you follow this topological sort. And you know beforehand that this is an evidence that is there, and you know that this is what it's going to be. So what you can do is, even before you hit that evidence random variable, you should try to make use of this. So if you look at it, when you're sampling the non-evidence variables, what are you doing? You're just looking at its parents, right? So maybe like the alarm network is a bad example because what the particular query we are having, it had just a J and M in the leaves, right? So maybe suppose you had something further down, okay? There was something even further. This was fine, okay? Because you will see the evidence. Or maybe alarm network is a good example for this. So you will see this evidence, you will fix J and M, and subsequently the next random variable here, so maybe let's say J prime. So now when you sample from this, you will say you will use the distribution probability of J prime given plus J. And here you will use probability of M prime given plus M, right? Because that's the evidence that is fixed. Now, but these variables B, E, and A, they are not going to make use of the fact that J has to be plus J or M has to be plus M. But actually there is a dependence, right, in the network. So, there is possibly a different distribution that you need to use to sample your B's and E's, taking into account that finally what you're going to get is a plus J and plus M. So how can you do that? The likelihood weighting does not account for that. Here you're just going to sample from A given B, E. You're not going to make use of J and M, plus J and plus M, right? So that brings us to Gibbs sampling. So Gibbs sampling is one of the really successful sampling approaches, and it's like very popularly used in a lot of these machine learning methods, like basically probabilistic methods. They make use of Gibbs sampling. Right. So I won't be giving you a proof of why this works, because it's slightly involved. It's a very detailed proof. But what I want you to see is like how to use it. Okay, what is involved in using Git sampling or in implementing Git sampling? What goes on, right? So here the procedure is kind of like what we have done, but what you do is you first fix the evidence random variables. So you fix the evidence. Okay, so you're doing something like this. So probability of, let's just say, X given E, right? This is something that you want to evaluate. So maybe let's just call it Q itself. So probability of Q given E, and there are many other random variables X. So what you do is now you fix the evidence. So E1 equal to E, and so on, EK equal to EK. All these you fix beforehand. Now what you do is you run a loop, okay? And what you will do is you fix all the evidence and you randomly initialize all other values. Randomly initialize q and x. Okay, so what this means is I'll pick one of the values. So q can take q1, suppose it can take q1 to q5. I'll fix some value here, so maybe q1, and I will take x equal to something else, maybe x1. I'll just fix it randomly, okay, and or maybe arbitrarily, just pick something here. Now what you do is pick one of the pick one of q and x. Okay, so maybe q, so this generally, let's say it's q1 to qk, and maybe x1 to xn. These are the remaining random variables, right? So right, I hope this is clear. I don't know if the notations are getting confusing. So by q I mean, like, you have a set of random variables q1 to qk, and e is, say, okay, so k and all these things can get confusing. So e1 to, let's say, el, qk. Okay, so e1 to el, and here you have x1 to xn. And when I say you pick q first randomly, so randomly initialize q1 up to qk. You also initialize x1 to xn. So this is going to take some particular value. So q1 will take some value, maybe like small q1, and this will take a value small qk. So fix this. So do the same for all of them. So let's just say, yeah, just initialize it to any value. Now pick one of these random variables. And what you do is, so suppose you picked a variable, say q1. So say q1. Okay. Now what you do is you draw a sample from probability of q1 given everything else. So q2 to qk. So this is what you already initialized. So this is q2. This was a value qk, and then you had x1 equal to x1 and so on. This is the particular values that you fixed. So this was x1 up to xn. Okay, and also the evidence. So evidence is fixed. It's e1 to ek equal to en. Okay, so fix all this and you generate a sample from this distribution. So I will tell you, like, how do you find this distribution. So you draw a sample here. So let's call this, now this is the new q1. Okay, and you keep doing this on a loop. So again, now you pick something that you haven't already picked. So maybe you pick x1 now, but this has to be a random picking. So it shouldn't be a sequential picking. So you pick something randomly, and you keep doing this, right? And so the important thing is you should be able to circle through all the random variables. Okay, and you keep doing this many times, and in the process, some things will get updated and so on. And maybe you visit all the random variables q1 to qk, x1 to xn, and again do this. Okay, so basically you keep doing this many times, and finally you will get a value of q1 to the last value that you have, x1 to xn and e1 to el. That's what you return. Okay, so this is your sample. So basically you do this loop not once, not m plus k. So this is m plus k random variables, right? Not m plus k times. You again repeat. After you finish all this cycle, you again keep doing this. You keep doing this many times. And finally, whatever you get in the end, that you return. Okay? So it seems like a very strange way of doing things, right? Is the procedure clear? So do you want to take an example maybe with the alarm network and see what this means? Okay, everybody is very silent.
It's clear, ma'am.
It's clear? Okay, so let me just tell you what it means when we are trying to evaluate plus b given plus j and plus n, right? This is what you want to evaluate. So this was the network. You had A. So I think it's useful to just see what this algorithm means here. So what you will do is there are 5 random variables. Now you're trying to evaluate this. So you fix j equals plus j and m equals plus n. This is going to be fixed in your sample. Okay. Now what you will do is you will pick, so there are 3 remaining random variables, b, a, and e. So what you will do is, now maybe you picked b. So you pick B, and what you do is you will draw a sample from P of B given A, E, and plus J plus N. Okay, and in particular, these are also something you have to fix. So plus J and plus N, this is fixed. Now B, A, and E. So maybe this was fixed as B dash, A dash, and E dash. Okay, this is what it was fixed. And so what you will do is you will uh, pick B from this distribution. Okay, and set the value of B. So maybe this was, let's say this was B double dash. Okay, so your current set of values is B double dash, A dash, E dash, plus J and plus N. Okay, and now what you're going to do is maybe you pick E. Okay, and what you will do is you will draw a sample from P of E given B double dash, A dash, plus J plus N. Okay, and now let me call this E double dash. So your sample is now B double dash, A dash, E double dash, plus J plus M. This is what is a temporary sample in some sense. It's in the intermediate stage. This is what you got. Now you will pick A. So we didn't cover A. So B, E, and A now you will do. And maybe in the same manner. So you'll pick from A given B double dash, E double dash, plus J plus M. So maybe you got an A double dash. And so now your sample is like this, right? Plus J and plus M. Now again you'll keep doing this. So now you will, again, maybe this time you picked E first, right? And what you will do is you'll sample from E given B double dash, A double dash, plus J plus M, right? And this keeps going on many times. Okay, and at the end, whatever you get, that is one sample. So a lot of effort to get one sample. But turns out that this actually does well in terms of the estimates you get. Okay, so there are guarantees on this approach. So just to give you some sense of what is going on behind, there is an underlying Markov chain that this method is constructing, and these probabilities are behaving like the transition probabilities. And so whatever you're getting is a sample from the steady state distribution of the Markov chain. So just a very high level idea of what is happening in Git sampling. So more generally, these kind of methods are also called Markov chain Monte Carlo methods because there's an underlying Markov chain. Okay? So maybe let's just see it in action, or there's one more step that I had to mention, right? How do you compute these, right? You wanted to evaluate a query, you wanted to do this. Now inside, there's one more probability that you have to estimate. Okay, so there's one more probability distribution you need. So inside an inference, there's one more inference. What's the point, right? So this is probably a question that bothers. But what happens here is this is a very specific kind of an inference problem. It's a very specific kind of query, which is actually not too hard to do. Okay, so do you have any thoughts on why it's not hard if you just look at this probability? Any guesses why this is not too hard to do?
We can use the join and other operations.
Yeah, you can do that. So yeah, what you're saying is we can use variable elimination, but the whole issue is variable elimination is not always easy, right? Doing a join, normalize, and if the networks are large, this is not generally guaranteed to be easy. And that's why we are going for sampling, right? But now within sampling, if you're going to again do variable variable elimination. So what's the, you see, there's some cyclic issue happening there, right? What is the advantage, right? Advait, to understand the issue? Yeah, so this probability actually, yeah, it's not as hard as the general inference queries. So you don't even have to use variable elimination here. So it turns out that way. So let's just see why it's the case. So I'm just going to take maybe about 3-4 minutes more to wrap this up. Okay, so let's just write this down here. Okay, so maybe I'm trying to evaluate something like this: probability of A and B given the value of A, E, j and m. So this is a fixed value, e, j equal to j and m equal to small m. I'm trying to evaluate this. Again, I need this entire distribution. So I need probability of b equal to b for every value of b. Okay, so this is what I need. So now, just by going with whatever we've been doing, right? The conditional, this is a conditional distribution. So what this is equal to is a equal to a, then e, j, and m by the sum over all possible values of b, right? So a, so sorry, this time this is b, a, e, j, m. So these are all fixed. A, e, j, m are fixed, and the only thing that changes is b. Okay. Now here again with the structure of the network, what we would write is this is probability of b, then probability of a given b and e, times probability of j given a, probability of m given a. Now there's a summation here, which is again the same terms, probability of b times a given be. So these are like different values of b you have to take and sum over, and j given a and m given a. Okay, so all these a, j, m, these are all fixed, right? And e also, a, e, j, m are fixed. Okay. Now, can you simplify something here in this expression? Does something happen to make things simple? Can you do some? Can something be done here?
Ma'am, did we miss the term P of E?
P of E, correct. That's also there. So there's a probability of E, and here also there's a probability of E. Yeah, thanks for pointing it out. Yes. Yeah. So can you simplify something here from these two expressions? Something cancelling out.
We can take out the common things which are independent of b out of the solution.
Yeah, exactly. So in fact, all these terms can be cancelled, right? So probability of j given a. So it's the same term which comes on both the numerator and denominator. So these two you can cancel. You can cancel these two. You can cancel these also. So all you're left with is the terms which involve b that you cannot cancel out because there's a summation here over b. So these terms are independent of the summation. So that's why you can just cancel it out. So what you get is just this, right? So this is a very easy computation. So what you do is you take for every value of b, so let me call this b dash, so just so that it's clear. For every b, what you do is you compute p of b times p of a given be divided by the summation, right? It's a normalized operation. This is all that you need. It's not, you don't have to do a join over every random variable and eliminate, and you don't have to do all that, right? So what is happening here is, as more generally, if you're trying to evaluate this kind of a query, b given something, then what you do is you will have only these terms which involve b, only the conditional probability tables which involve b you need to consider here in both the numerator and denominator. Everything else is fixed. Okay, so there's a very specific form because here there is just one random variable. So that's what makes a big difference. There's just one random variable here, and here in this part there are all other random variables and they are all fixed. Okay, so this kind of a query is easy to do because of this. There are no hidden variables, right? If you remember, like the purpose why we had variable elimination was, if there are a lot of hidden variables, you want to iterate over the whole network, that becomes hard, and so you're trying to simplify things. Here that's not the case, no hidden variables, and in this part there's just one random variable. So it's only all the tables where that random variable appears, you just take this product and divided by, the normalization has the same thing. Okay, because everything else cancels out. So that's why this probability which arises in this intermediate step, this probability distribution is not hard. It's easy to compute. You can keep it ready and then you can just draw these samples. Okay, and yeah, of course you need to use this particular values from your intermediate samples itself. So maybe I'll just wrap up with a demo of this. So I'll also share these codes with you. so that maybe it gets clearer when you see the code. So again, for the same network, what I did was I computed it with Gibbs Sampling. So basically, I fixed these samples. Now there is these 3 random variables. I mean, it's all hard coded because I just wanted to focus on showing this example. You can do it more generally for any basenet. And so what you do is you pick one of the random choices for each of these random variables, right? So sample B is a random pick from these two. Sample A is a random pick. Sample E is a random pick. Okay. And what I'm also, why did I do this? Int. Okay, so this is bad coding. I don't think I needed to use this int anywhere. Okay, so what I do is now I come inside this loop. Okay, so there is an outer loop for the number of samples, and there's an inner loop which is within each sample, how many times do I loop? Okay, so I fixed some large values here. So something like 1000 is what I fixed here. And so this is an input to this function. And then what I did is I picked one of these variables randomly. And this is where I am computing these conditional probabilities. So basically these probabilities I compute. Okay, so yeah, there are a couple of values to be computed here. And so this is the new distribution I have. Okay, so the conditional distribution, the intermediate conditional distribution, and then I draw a sample from that. Okay, I draw one sample. And now this is the new value of B. Now, same thing. So I come back here and I draw another random variable. So I remove, this B. I mean, if I chose B, now I want some other random variable, right? So I do this many times. And then I again repeat this loop. I bring back all the options and again make more choices. Okay. So, and the final sample is the last value, right? So you can see the evidence is fixed. Okay. So now let's just run this. So maybe I'll just run all the methods so that you just get a sense of what happens here. So I'm just running all the sampling approaches we looked at. What did I do? Okay, fine. Okay. Okay, fine. Okay. So the number of samples are set to different values. This is something that I was just experimenting with and to see where I get a reasonable estimate. So like I said yesterday, I computed this probability by hand, and this was the value I got. So plus B given plus J plus M. For this base net, I got it as 0.28. Okay, so what I did is I just ran it, with different settings of the number of samples and just saw where, I get kind of, a same estimate every time I run. So that's how I fix the number of samples. So in Git sampling, what I'm doing is I'm just using 500 samples, but the inner loop runs about 1000 times. Okay, so let's just run all of them. So here you got the estimate. So let's look at Git sampling. So the estimate given is about 0.27, right? And so prior sampling gave a very bad value because the number of relevant samples was low. And similarly, rejection sampling gave a kind of reasonable estimate, not too bad. I think here prior sampling is also fine, right? Because the number of samples is large enough. But if now what I want to just say is in terms of the times taken, right? So the worst is rejection sampling because I waited till I got 1000 samples. I discarded everything else. And Gibbs sampling is also, it takes some more effort because, they're doing a lot of work to get one sample. But in terms of the final estimates, it's actually, if you do this many times, you'll see that it's kind of, the variance is not too much. Gibbs sampling kind of gives good estimates every time. Okay, so yeah, sorry, I've taken quite a lot of time. So what I'll do is I'll stop here, and I'll also share these codes with you so that you can play around with it, and maybe you should also try. So these are all like very applied things. So you should try to write code for this for some general base nets. Take any of the other networks we have looked at, maybe in your assignments, and try to write code for sampling. Trust me, it's going to help you later on, even in the industry. These are things which get used a lot. Okay. All right, so we'll stop here and I'll just hang back if there are any questions. If not, see you tomorrow.